Welcome. This video is going to go over a skill that is required in AP Physics C that I affectionately call superfractions. College Board, I do not think, uses the term superfractions because I made it up. Actually, one of my students several years ago coined the term and it just stuck. So what AP does look at is this skill, which they've labeled 2D, and it's called functional dependence. And superfraction is the technique or the approach that we're going to use to solve these types of problems. There are many other types of skills that the AP Physics C exam is going to want you to show that you know how to do. So there's a bunch of these that are listed for you to look over and we'll practice, and there's weightings to these. And this is on a different handout, but we're going to be focusing in on these functional dependence problems, which I'm then saying we're going to use superfractions to solve. And this is when we need to predict new values or factors of change of physical quantities using functional dependence between variables. So just really key on this factors of change aspect. I think that's a better way to describe it than functional dependence. But that would be like, if I double this, then what factor does some other variable change indirectly due to that? So if I was going the driving school thing, like when you're learning to drive, that would be if you were going twice as fast, by what factor does the distance it takes to stop change? So if I'm going twice as fast, then it takes, oftentimes people know, 4 times the distance to stop. So you got to make sure you guys are keeping space between your cars when you're driving. Okay, so let's go over to this handout. So we're going to approach these with a few different types of examples here to show you how this functional dependence skill takes form using superfractions. So let's first look at this problem. There's a ball that's dropped from rest from a height h, which it falls then over a time t, and saying by what factor. So that's what's going to cue us that this is a functional dependence problem and that we need to use superfractions. So by what factor does the time change if the ball is dropped from double the height? So you can see that something's being doubled, and then we want to see how something else changes and by what factor. So the first thing we're going to want to do is identify the underlying equation that's involved. Okay, so from here, we want to show that this equation best fits this situation. We have from rest, which means that the v naught is equal to 0, so that's good to have in an equation. We want a distance, or height h, in this case delta x will be that height h, and t to be in there, so that we then can use an appropriate equation, right? Something that we need to know here is that this is a free fall problem, so that means our acceleration, which we can also use the letter g for gravity, is 10. That's when it's in free fall. So this is an appropriate equation for this context. So what we want to do next is isolate the variable in the question. So what's the thing that we're trying to see by what factor it changes? And that's, does the time change? So by what factor does the time change? So in that case, then, we're going to rewrite this equation with the variables that are given, h, my acceleration could be g, and I'm going to rearrange this to isolate t. And so here I get the same equation, but isolated for t. Once I have this, then I can make our superfraction. So what the superfraction is, it's going to take this expression, square root of 2h over g, and we're going to set the newer version of this with the doubled height over that same equation, but in the older version, which is just going to be the 2h over g as it is. So let me show you what that's going to look like here. So we're going to set the old, which is this, the 2h over g, that's the original one, over the new version of this equation, which would have the double the height. So it looks kind of scary, but we can do some fun dividing out here. So then that would mean that we can divide out the 2 and the g with the 2 and the g and the h's, and that leaves this extra 2 up here. And that 2 is under the square root. So that means that our factor for time that it's going to change by is going to be root 2. Try another one. These are fun. A ball dropped from rest and free fall over time t, same problem as before. But after this time t, it reaches some speed given as v. We want to know by what factor does the time change, once again, but for the ball to reach a speed that's 3 times as fast. Okay, so let's think about the underlying equation here. So we've got this equation. Now, why is this equation the appropriate one to use? It's because we again have, sorry, seems to be jumping around on me a little bit here. We have the from rest, which is v naught. The free fall again is going to give us our acceleration as 10, which is due to gravity. We have a time t, and now we have a speed v instead of that height. So the better equation that has all 4 of those variables involved is going to be this one. We're going to isolate time in this question because that's the variable that we're trying to see by what factor it will change. And in order to do that, pretty simple algebra here, we're just going to isolate t, which is going to be the ending speed v over g. When we write the equation with 3 times the velocity over g, set over the original one, which was just simply the original speed v over g, then we see here that everything divides out, leaving with simply a factor of 3, which means it's going to be 3 times the time to get to 3 times the speed. This was a pretty easy one. Let's keep moving on. Number 3. A ball rolls down a ramp, from rest I should say, reaching a speed v after traveling a distance d. And it wants to know what multiple of d will the ball reach if it were to roll to a speed that is twice as fast. So by what factor, what multiple of d, those are really the same command that it's asking us to do, these superfractions. And so with this one, we're going to have to identify the appropriate equation. And so with this, what it looks like, we're going to want to use this from rest. There's v naught, there's an ending speed v, we have a distance d, and we know if there's the same ramp involved, then that's going to yield the same acceleration. So this one is going to have this appropriate equation here because it has both the beginning speed and ending speed, the same acceleration, so that should divide out. And we have the distance d, which is going to be what delta x is. So if we rewrite this equation with the given variables, then we're just going to replace delta x with d, and obviously v naught is 0. And so we want to isolate the variable d here because that's what we're trying to figure out by what factor or what multiple of d it's going to change by when we go twice as fast. And so if we do some algebra there, then d is going to be equal to our v squared over 2a. Okay, so that's then going to allow us to make the superfraction, and the superfraction is going to be this v squared over 2a, and that's going to be in the denominator. And then we're going to put the new version of this equation with the double the speed. Notice I had to put that in parentheses, so we're going to have to distribute the square, which is going to give us a 2v, quantity 2v squared, right, is equal to 4v squared. This is a very simple algebra mistake that people make very often, regardless of what math level you're in. It's just a careless error. So we got to be really careful there. Okay. So then that's going to yield a factor of 4. So let's look at how we got that. We divided everything out. That leaves us with this factor of 4 that we got by squaring that 2. So it'll be 4 times the distance. Now I didn't put 4d there because it said what multiple of d, so it's just saying what do I need to multiply d by for the speed to be twice as fast. It's got to be 4 times the distance. And if you remember, this is our driving lessons, driving school, driver's ed, whatever you call it. That was our question. If you're going twice as fast, how much distance do you need to stop? It's going to be 4 times the distance. So whatever it is, double the speed, triple the speed, we got to square that factor in terms of figuring out by what factor the distance would increase. So if you're going 3 times as fast, it's going to take you 9 times as far to stop. Keep that in mind, kiddies. Okay, last one here. Same thing, a ball's rolling from rest down a ramp over some distance. We're going to call x instead of d. They get to choose if they write the problem what letter they want to use to stand for these things. So they're using x here. In time t. So by what factor does x change if it's allowed to roll for this for time 3t, so 3 times the time. Okay, so the information we have here is going to be then v naught x t and a the equation that fits that situation would be this one, because it has our distance, v naught, t, and a. We're going to isolate then x, but really we're already done, right? That's because x is already isolated, right? So subbing in v naught is 0, we now have our equation. X is equal to 1/2 at squared. So it's already isolated. We don't have to do any other algebra. Now we get to set up our superfractions. So we have our 1/2 at squared, the original one in the denominator, and then we're going to put our newer version of that in the numerator. You can see I put 3t in the parentheses for time. Again, we got to distribute that square. So that's going to give us a factor of 9 when I rewrite this out. So you can see 3t squared, when we have 3t in parentheses, will give us then 9t squared once we distribute the square. So now everything divides out, leaving this factor of 9. And so that will be then 9 times the original distance if you were to do 3 times the time. Thanks, everyone.